Right, thank you very much. Thanks very much, John. Thanks to everybody for being here, and sorry about the interruption. This is perhaps very appropriate given the theme of my talk, which is communication with uncertainty. I'll get to the how it connects in a moment, hopefully, but let me just say that this is an outcome of a lot of joint work. We started with Brendan Juba, who is a student here, and then expanded to include a whole lot of others that are listed here. I'll try to explain to you what I want to talk about, but consider this talk itself as a question. What should I talk about? Is this a mathematically well-defined question? We don't think of this kind of a question as something that we should be capturing with mathematics, but what is the reason for that? Can I not, there's information in my head, there is information you may be seeking. Why is it that we cannot cast this question in the information lens and also answer it and try to figure out what would be the, say, optimal talk to give under these circumstances? Can we abstract this question? What kind of ingredients would this answer involve? One of the fundamental motivations for this line of work was to understand human communication. And somehow the fact that it is very different from design communication. Okay, and human communication does have notions of efficiency, reliability, and perhaps something that we take for granted in design communication is a notion of utility. And all of these ingredients somehow play a role, but they all have different interpretations in the two settings of human communication versus design communication. So I would like to understand, where would a theory come from? So communication and computing have very rich theories. So here at the bottom, we have, we have Turing and Shannon, who both set off some really profound theories. I really appreciate them very much, and I do believe and I work with these theories extensively. Yet I feel that these are theories that are very well separated. One talks about communication, the other talks about computing, and together they talk not about the union of the two sets, but rather the symmetric difference of the two sets. When we come to points in the intersection of the two, neither theory, so each theory seems to contradict the other. And let me try to explain why that is the case. There's a few other things that I mentioned in the slide, but let me skip ahead and just talk to you about why these theories seem to be so contradictory, in my opinion. Now, the computing theory, fundamental principle behind it is the notion of universality. You should be able to program your computer to do whatever you want it to do. And it can look like whatever it wants to look like. You want to buy a PC and make it look like an Apple, you can do that. You want to buy an Apple, make it look like a PC, you can do that. And there's a resulting phenomenon is vast heterogeneity of devices. Okay, so we really I do not think of even two objects that I own, computing devices that I own, as somehow being clones of each other. And I don't think I can actually, we're way past that point where we could arrange for that to happen. Each one tends to have a huge amount of context that really separates them. Communication theory, and this is very much encouraged by the computing theory. So I want to say that, stress that this is not an accident. The fundamental principle was we want to strive for universality. Communication theory tries to come up with a very clear separation between what is common knowledge to sender and receiver and what is information that's available only to, say, the sender, private information with the sender, which they want to send over to the receiver. And there's very little of continuum of this motion. So very clearly define what's agreed upon and what's not. And then we build encoders and decoders on top. We build compression devices, all kinds of communication protocol. And all of these protocols really tell you, do not program your device, because if you start programming the communication ingredients in your devices, then you will be unable to communicate. So what the theory would really like is a homogeneity of devices, which sort of goes against the heterogeneity promoted by the computing theory. And this is the sort of inherent separation that I want to talk about and want to ask the question, is there something else we could have done? And we do know that humans do tend to communicate and compute, think, and they tend to use that to complement each other, to enable each other, rather than this current mode in which our systems are built, which is to let each one of these theories negate the other. So what are these ingredients in human communication? Can we try to understand them using the same old lens as we would use, using some combination of the theories of Turing and Shannon? So here, they've been sort of, I've been working on this theme for about 15 years now, and there's two broad classes of results that we have here, and I'll try to tell you a little bit about each one. One of those tries to understand this notion of how do children learn to speak, or they don't learn to speak by, say, taking a course which tells them how to cry. They just do. And from this theory emerges a way by which we can somehow communicate. And we have not been taught to speak. Instead, we learn to speak by actually speaking or by communicating. So you learn to communicate by communicating. And this was the focus of some works that I did with Brendan Juba here and Oded Goldreich. And what we asked here is really what is possible. Is a certain communicational task even achievable? Let me try to give you a brief flavor. I added this one slide because I noticed that the scope of this workshop was significantly broader than I anticipated, so I tossed it in. So one question that we asked is, what does it mean to communicate meaningfully? So, I am sending you bits, you are receiving bits. Isn't that communication? We want to say that's not the end of it. We want to see what you can do with it. One good way of formalizing this question might be that I want to send you an algorithm and you want to execute the algorithm, except we haven't agreed maybe on a programming language. Okay. Can I somehow send you the algorithm? Maybe we interact for a little while and then you stop and you say, okay, I'm done. Now I'll go ahead and be able to execute this algorithm. Is this achievable? And the first thing that we noticed was once you formalize this question carefully, and in particular, try to incorporate the fact that you do not understand the programming language that I'm working with properly, then this is not something that we can actually achieve in finite time. So it sounds like very, the typical bad mathematical result, but that was not our goal to achieve a negative statement. Rather, we wanted to explain what it is that allows us to actually communicate meaningfully, what is allowing children to do it. And in order to get to that point, we gave something which I'll sort of, this is an example of the kind of definitions we came up with. Roughly a weaker definition might be Bob really does not care about the algorithm A per se, but wants to know what would the algorithm produce as output on a particular input. So maybe Bob has a large number X and he wants to find its factors. Alice claims to have a quantum algorithm which will be able to, quantum computer which can solve it, or quantum algorithm. And Bob is not interested in the algorithm, is really interested in the factors of this number. Well, that is something that we can actually achieve, even in the absence of a common language to start with. And the main theorem with Goldreich and Juba was that there are some technical conditions that you have to put, but you can basically allow Bob to infer the answers A of X as long as Bob has the ability to verify it. So even in the case where Bob is only interested in the value of the function computed by A on a single input, it is not that you can use any input and be able to communicate its value, any function communicate its value. You can only do it provided you have the ability to verify the computation somehow yourselves. You can use Bob as an assistant in this verification. That's fine. You can use Bob to help you. Bob might actually be sending you an algorithm, and maybe Alice is able to, Alice is sending Bob an algorithm A, and Bob may be executing it to compute A of X. All of these are possible, But whatever is possible at the end, Bob will be able to determine A of X and know it's correct. But the knowledge that it's correct, rather than being a consequence of this ability to communicate meaningfully, is the means by which we are communicating meaningfully. When we realize that some communication is when we are not getting a verifiable answer, that's when you should understand that some misunderstanding is occurring in the communication, and it allows you to search for other meanings for the words that have been sent. This, by the way, is a mathematical theorem. We are not postulating this as a thesis, but on the other hand, it comes with a definition which allows this to be a valid theorem. The definitions put some restrictions, but we believe that the restrictions are pretty meaningful. These do capture the concept of a person who completely alien to us comes to us and starts to converse with us, has no idea of the language that we are conversing in, but is eventually learning the algorithm, the language, or maybe we learn the alien's language and communicate the answers to them. We are agnostic to either of these possibilities, but at the end, the person who's seeking utility from the conversation will be able to gain utility from the conversation. Okay. So that was a very quick, compressed explanation of what we did in this piece of work. And that's, to me, the analog of what we would call the computability version of this theory. It tells us what are the limits achievable with vast amounts of communication. There is some discussion of efficiency in this context, but not a whole lot. What we turned to pretty soon after that was this a second ingredient in human communication that seems to be unmodeled and uncaptured in the classical theories of communication or computing. And this is the ability to leverage large and uncertain context. And one of the goals of my talk is to try to explain to you, what is context, how can it be large and uncertain, and why would you want to leverage it? But going back to this example of this talk today that I'm trying to give, this is a talk that assumes a huge amount of common context. It assumes you know some English, it assumes you know some mathematics, it assumes you know probably large amounts of CS theory. It probably expects social information, geographical information, etc., all of these things. And yet we didn't exactly sign a contract saying these are the ingredients of English and math and TCS and social information and geography that you should know, right? What we are saying is, look, here is a space, there's vast amounts of uncertainty in what may or may not be known, but I cannot live without this common context. It's not that I'm going to teach you English and then math and TCS and then get to the punchline of my talk. I'm going to assume it, and even though I'm not certain what's going on, I will be able to use this thing, hopefully, to send you some information that you seek. Right? So how can you make communication efficient using context has been the theme that I want to talk about for the rest of the time that I have, about half hour. All right. Context and communication, how do you capture it? So before I get to that, how should you think about it? Like I stressed already, this should be viewed as huge, huge, huge. So large that we are not going to sit down and deliberate about how much of it do we have in common and how can we resolve the misunderstandings that we have. It is inevitable that there is going to be some things that I'm assuming that you are not going to be aware of, and some things that you're going to be aware of that I'm not going to be aware of. And it may even be something that is not strictly needed for the communication. I could, in principle, get around it. But if I do that, then communication will be very inefficient. If I can assume that you and I are perfectly aligned in context, communication would be much more efficient. But what we also seek is some graceful degradation. Even when the setting where context is not shared perfectly, we are able to weaken the communication abilities, the length of the communication only slightly, but allow the players to communicate and perhaps and definitely much more efficiently than if we had ignored the context and tried to do the communication. Okay, so those are the kinds of phenomena that we are looking for. And what I'll try to do in this talk is give you a few examples of such phenomena. But in order to do that, I have to formalize some of these questions. I'm not going to give you a general theory formalizing everything. I'm going to give you anecdotal examples of here is a communicational task, where here is what context is, and here is how it is used in order to improve communication, and whatever we know about how much we can relax the assumption that the context is shared perfectly. Okay. All right. So so far, what we've done is some settings, and maybe these are toy settings. Now, in order to get to this point, it took us a while to get to this thing, but what we realized much later on was a model for this kind of communication task has already been established. This is the model of communication complexity proposed by Yao. And indeed, in fact, one could argue that the original goals of this model was really to capture this kinds of conversations and computation and communications, but for it's a sort of a historic coincidence that this model has been hijacked mostly to prove negative results and to say things cannot be done. Today we'll try to say what can you do in this model and how can you use this model to explain efficiency in communication. Now, what this model suggests is describes the following. Alice and Bob are two players who are trying to communicate with each other. They have two private inputs, X and Y. And they wish to not exchange all the information. So X for this talk may be all the information that I have. Y may be all the information that you have. And you have some goal, which is some joint function of X and Y, but it does not require you to know all of my, me to do a core dump of my brain in order for you to be able to get this utility. You would ideally like it much faster using fewer bits of communication. So Bob is interested in computing this function f of x, y. It's a function of both the inputs, and we would like to see, can you do this with much less communication than exchanging x or y from one side to the other. Okay. In the specific, in the results that I will talk about, we will talk about communication complexity of a function, which is the number of bits that are exchanged, by the best possible protocol which achieves this task. We will allow both players to have some common randomness, and often our results will be characterized by where can we say some number of bits. Communication is a small bounded amount and does not depend on the length of x and y as they grow. All right, this slide I will skip, but there's for those of you who choose to look at these slides later, here's a few examples of some very easy communication problems that can be solved on large inputs, unbounded length inputs, with a fixed constant amount of communication. And these are, these examples, one could say, motivates our kind of a question. The main punchline, the reason I flashed the slide, is just to highlight the following statement, that communication with a focus. By focus, I'm saying, the fact that we are only interested in f of x, y. I don't care to know all of x. Bob doesn't need to know all of x. Alice doesn't need to know all of y. They're only interested in f of x, y. Well, this could be much more effective in the sense that you can have much less communication than the entropy of x or the conditional entropy of x conditioned on y, etc., all of which might have been considered necessary for communication. So here's the setup then. Communication with uncertain context. What we want to think about is Alice and Bob might have some context in the communication. In this example itself, we can take all the things that were introduced by Yao's model and throw them in as explicit parts of the context. Alice knew the function that is being communicated. Bob also knows that function. They both had some common randomness, which said, oh, look, whenever we want, we have access to these pure random strings, and we can utilize this, and we don't even have to exchange it in order to do the communication. Incidentally, all the examples on the previous slide really depended on the randomness. If you didn't have this common randomness, the amount of communication would grow with the lengths of the inputs. And finally, they could also have some knowledge about the distribution from which X and Y are chosen. Maybe they're chosen jointly. Well, if that's the case, Alice and Bob know this context. We have seen many examples of problems where knowledge of these contexts, certainly knowledge of the function f, the common randomness, the distributions, is very, very, very helpful in reducing the communication complexity. If we did not have this, if we did not have this context, if we do not try to use the context, there'll be huge amounts of communication. All these blue arrows, but once you throw in this context, which is common, a lot of the communication goes away and you're left with a very small amount. And what we would like to try to do in this talk is to say, well, maybe there's some flexibility in these kinds of contexts. Okay, maybe we can allow Alice and Bob to work with functions which are not really the same. Maybe they're similar functions, or maybe the randomness is not exactly the same. Maybe they are noisy copies of each other. Maybe the probability distribution that Alice thinks the message is coming from is different from the distribution that Bob thinks the message is coming from. If all of this happens, we might be forced to have some extra communication because we are dealing with uncertainty in the context, but it should not be as large as we would want to work with if there was no context at all. So hopefully this is a little bit more precise, mathematically well-defined. And let me try and explain to you what are but this, unfortunately, again, is too broad a setting. We don't have general results of this nature. What we can try to do is consider specific communicational tasks in which we can introduce these ingredients, make them different, and then try to say, what's the effect of the uncertainty? Okay. The first of these examples is one of the most basic tasks in all of communication, which is compression. Okay. So what is compression as a problem? The goal of Alice gets an input X, Bob's goal is to output X. Okay, the function that Bob is interested in computing is just X, nothing sophisticated about it. We just said, oh yeah, there's nothing, this is not what Yao's model was intended to capture, but it's not that it wasn't allowed in the model. We would think there's no way to do anything except communicating all of X in whatever is its native representation, hoping that Alice and Bob already have agreed on this native representation. But if we make some common context assumption that Alice knows the distribution from which this message X was chosen, and Bob also knows the distribution from which this message was chosen, then we can actually compress the communication significantly, and we can compress the expected communication down to the entropy of this string. Okay. Now I'm talking of a single shot compression problem. Alice gets a single message from this distribution and has to transmit it. There is no assumptions about the distribution except it's known to Alice. It's also known to Bob. Okay. So the solution for this problem would be Huffman coding. This is the one that gives you the optimal algorithm for communication. And before I describe the solution, I won't describe the solution, but I just named it. Let me at least formally define the problem. So what's the problem? Alice and Bob, let's say, have a distribution on some space. Let's say this is a space of n-bit strings. They both know that the message is going to come from this distribution P. They agree on an encoder and a decoder. Now Alice gets this should have been X chosen from 0, 1 to the N. Sorry about this. This should be 0, 1 to the N. Sender gets a message to transmit to the receiver, and the receiver will get some compressed version of that message. And they've already agreed on the compression, the decompression, so this is fine. So some amount of pre-agreement, etc., is being allowed in this model. And now, once the receiver gets this thing, this is noiseless information transmission. So the receiver simply decompresses the string, and we are hoping that the string that the receiver decompresses to is exactly the message that the sender wanted to send. Okay. Now, the performance measure is usually the expectation when you choose X according to this distribution of the length of the encoding of X. And this is the quantity that is known to be very tightly bound by the entropy. Notice that if we just ignored the context, we could just send X and its encoding and decoding function could be just the identity functions, and we would have an expected communication length of n. But using the context, we've compressed things down to the entropy. So for this talk, you might want to think of entropy of distributions we're thinking of as being some fixed constant, let's say 20, whereas strings are of length, 200 kilobytes or whatever. Okay, so this could be much, very, very, this is very effective compared to that. What can you do when there's uncertainty in the context? Well, first, how do you model uncertainty in this context? Well, the modeling is fairly simple. Sender has a distribution P, receiver has a distribution Q. But now they don't get to design their encoding decoding schemes after these distributions are given to them. They should pick their encoding and decoding streams before these distributions are given to them. Encoding, however, can depend on the distribution, and in fact, it should. So when you compress, you should say, well, I think the message comes from the distribution P. I would like to be able to compress it down to its entropy, which is, or as much compression as I can get. But this is the distributional information that I'm going to use. Receiver will get whatever the sender sends, but when they're decoding, they can only use their own private information about the distribution, and they have to decompress according to that. We don't want the decoding to be always correct, but we would want it to be correct provided these distributions are close. Now, I'd have been happy with any definition of closeness which would have worked. This is a very, very, very stringent definition under which things work. So let me use it. It's a non-trivial definition. It allows P to be different than Q, which is already very impressive because no protocols really had this property. What's this measure? It says for any potential message, if you look at what Alice thinks the probability is, what is P of X, and what Bob thinks the probability is, these two should be off by some multiplicative factor, 2 to the delta, for whatever measure delta you choose. So for this talk, let's think delta is 10. Okay, so the probability that you associate between two messages should be off by a factor of about 1,000 for every possible message. So it's a pretty stringent requirement. I don't deny that, but it's allowing P to be not equal to Q. Question is, can you actually do communication with this? And what we know so far is the following, that again, we are expecting the minimizing the expected length of the communication. We can only do this so far using some additional shared randomness between the sender and the receiver. But if we do allow it, there are compression and decompression schemes which will allow them to basically lose 2 delta in the communication. There may be plus some constant, absolute constants depending on other parameters that I might have skipped. But they will be able to get to some measure that looks like that. And unfortunately, this actually expects Alice and Bob to have some pure random string that they share perfectly in common with each other. And in particular, this distribution should be independent of P and Q. This randomness should be independent of P and Q, but it does allow them to get very good compression out of it. One thing that you should realize from this, given the fact that I stress this, is in particular, all the classical compression schemes that I know, which are all deterministic, which can be implemented in some deterministic way. And we are not talking of computational restrictions over here. These are unbounded computing functions. All of those were deterministic, and hence none of them actually achieves this guarantee. So you do need something additional. If you want to ask the question, what can you do without shared randomness? We did answer it in we did give a bound, but it's not potentially not the right bound. It's some constant multiple of the entropy of P, maybe factor of 2 over here should work, plus the same delta, plus another log n, where recall that Alice and Bob are getting n-bit strings to exchange. So this is not something that I consider ideal because it is actually growing with the length of the input. And I would want ideally to say, well, it should depend on the entropy and nothing else. But we haven't been able to get that. Okay. All right. So a few words about I won't tell you how this compression scheme works. Just to say, what was the kind of protocol we used? It's a very natural sounding protocol. Indeed, a very natural form of communication is being captured over here. Roughly, the sender keeps sending longer and longer and longer descriptions of the string X that they have in some pre-agreed protocol described by E and D, till the sender feels that the receiver really should have got it by now. Which is, I mean, it's quite remarkable that I'm working with exactly this mode of communication today. I can't actually hear what you folks are saying. If you're saying anything, I can't see much except for a few faces on the screen. And what I do see is that, but at some point I'll just decide to stop, and that's exactly the protocol that is being analyzed. And we say, actually, I mean, this is how most language works. It's not like I'm discovering this protocol for the first time. Everybody communicates this way. You keep, expanding on what you want to say till at some point you feel that you should be done. That's how you write a paper. You don't get instant feedback on what you are saying to be able to say, look, I'm done. I can explain everything. Go away. But we do get a theoretical analysis of this protocol, which is kind of novel and unique and so on. I don't know if I mentioned this, but this was work done with Juba, Kalai, not Gil, Adam Kalai, and Sanjeev Khanna. All right, so I'll skip along and let me tell you about two other themes. In each one, I'll say less and less. A second theme that we explored was the notion that the function that is being communicated by Alice and Bob is that itself part of the context. Okay, so we do know that if for some functions, if the amount of communication can be much shorter than the length of X or the length of Y or the entropy, etc., etc. But this F is common context. But for our conversation today, we do not agree on what is the goal of this talk supposed to be. Again, I'm making an estimate, and based on this estimate, I'm giving a talk. You may have some estimate. You create some function saying, this is the most I can expect this speaker to tell me about. But odds are pretty high that these estimates are not aligned perfectly. Is there something that we can still do to deal with the setting? That's the motivation. By the time we come to the mathematical model, it becomes very precise, and instead of functions being distant based on whatever makes human functions distant, it's going to be something simple like having distance and so on, but still, that's what we're going to work with. So we're going to allow Alice and Bob to have two different functions in mind. And what we will aim to do is to get something which is, Bob usually manages to compute f of xy, and usually means under a certain distribution on x and y, where provided the original functions fa and fb that Alice and Bob think they're communicating about are themselves not too far from each other under this notion of x and y. Okay. Now, suppose fa and fb are within some distance epsilon of each other. I'll be pretty happy over here if you can get log of, 1 over log of 1 over epsilon as the distance between the actual function and your thing. So your error can be vastly larger, any function of epsilon, as long as this measure goes to 0 as that measure goes to 0. Okay, we'll be happy with that, but it's not trivial. Okay, in fact, there's significant gaps in the length of the optimal communication protocol and what we know about the length of the relaxed protocol right now. But we do get something. Okay, what do we get? Well, definitions are kind of tricky over here, but let me start with actually a negative result. If the distribution on x and y was really arbitrary, then there actually exist communication problems where, with perfect certainty of context, the communication would have been 1 bit long, exactly 1 bit. So we hear, this is not order of 1, no nothing, just 1 bit long. But in the uncertain model where you're not so sure of the communication functions, even though these functions are exceedingly close to each other, the communication complexity blows up to something like square root of n. Notice what is n? N is always going to be the length of x and the length of y are going to be n-bit strings. So if we want to ignore context, Alice could just send X over to Bob and say, look, go figure out everything yourselves. So n would have been trivial. Square root of n is as bad as being trivial. So this is really, really bad result. And it seems to happen because there's two measures of uncertainty. Alice and Bob already have correlated inputs, x and y. And on top of that, the functions are not exactly identical. If the functions were identical, that would have been great. And as a second theorem says, if the distributions on x and y were uniform, or you could take any product distribution, nothing changes. As long as x and y are independent, you could actually work with this uncertainty in the functions. And then there are some technical results which say exactly how these things behave. If the function has one-way communication, then you lose just a constant factor. If it has two-way communication, then you have an exponential loss, but nevertheless, it's still, constant communication goes to a new constant communication. Okay. So this is a second flavor of the kind of results that I want to talk about. There was a third topic over here, but I want to skip it and just briefly mention one thing which might actually connect to some of the other talks that we've heard so far, but it's still, it's not, I don't have any theorems. I just have a question that I want to pose, or a meta question. It's a philosophical question that I want to pose, but formalizing it mathematically would be very interesting to me. And this is about proofs in communication. And we've talked about it today already. It's a central theme in communication in the study of computing. We always talk about proofs, and I also feel it's very, very central to communication because proofs are what allow us to convince ourselves that we actually learned something from any interaction. When I can convince myself that, based on this interaction, I've learned something, that's when I make progress. And that any communication that has that power is what I call a proof. Okay. So these are very central concepts, and yet there's challenges when it comes to the communication of proofs. So what do I mean by communication of proofs? What is it that models a proof that we publish in journals and books? There is, of course, one element, which is this goal of this proof is to teach you something. I want to dismiss that for a moment. I mean, that's a very important goal, but even if you go back to the original goal, well, it should at least prove the theorem that it is supposedly proving. Is it really doing it? And my claim is it's not. Let me explain why with just metaphorical pictures. The standard assumption is, we have some small number of axioms, then we have some maybe modestly long theorem, and then the proof suddenly is the one that is explosively long, and that's the one that takes very long to discover and communicate, etc., etc., etc. The unfortunate truth is that things are actually far from the case. This is a claim that I saw in a book on discrete math taught to sophomores at MIT, which says that, by some estimates, a proof that 2 + 2 is 4 in ZFC would require about 20,000 steps. So this book is not going to spend 20,000 steps on proving everything from ZFC. Instead, it's going to use a huge collection of axioms, namely everything from high school mathematics. I feel that this paragraph sort of, perfectly captures communication with uncertainty over here. What's communication? Well, I could have given you a formal proof in ZFC of any statement that is in that book. I presume that could be done. I'm not sure exactly what kinds of statements are in the book, but I suspect it can be done. And that would be inordinately large, even in this pretty large book. On the other hand, they could compress it using this common context, which is high school mathematics. But now uncertainty emerges for the same reasons. I mean, did we actually agree what is high school mathematics? I believe that in this uncertainty is where most of the challenges with communicating, with writing proofs and making them understandable to the reader lies. I mean, so many times we've seen, we submit a paper to a journal and one author, reviewer says, great write-up, excellent, blah, blah, blah. And the other one says, nothing is comprehensible. Why don't they define whatever they mean, etc. All of that goes down to this common context. What did we assume as the context and how do we build on top of it? what does communication, how does this common context affect communication? Seems to be a very, very intriguing question. And I hope it'll be the thought of some future, the core of some future work. Okay, so I'll skip. So summarizing, I'm interested in communication union computing, but I worry that the intersection is the big challenge here. And there are many interesting problems like how do children learn language, how do we harmonize on context, etc., which lie in the space and need to be modeled. We can get to some of the mathematical challenges associated with these models by perturbing some of the common information assumptions. And when we do this, you find, some of these slight changes suddenly completely kill the model, kill the communication protocols, and others don't. But when they don't, we actually have to change the protocol. So for example, in the compression, Huffman coding doesn't work, Shannon coding doesn't work. We have to come up with some new communication compression algorithm, and that compression algorithm is even randomized, and so on. The punchline to me is that communication protocols are not continuous functions of the context. They seem to be very, very sensitive to what the context is, and this leads to lots of challenges that need to be explored further. Thank you.
Okay, thank you very much.